Welcome, AI engineers and data scientists. I'm AI architect Jayaprakash from Anaha Agile Systems Private Limited AI department, and today we'll explore one of the most critical concepts in deep learning, regularization techniques. This visual representation before you encapsulates the fundamental approaches we use to combat overfitting and improve model generalization. Introduction to regularization. Let me begin with the core principle. Regularization is a collection of techniques designed to prevent overfitting by adding constraints or penalties to our model during training. Think of it as a disciplinary mechanism that prevents your neural network from memorizing the training data too precisely, thereby ensuring it generalizes well to unseen data. In this diagram, you can observe three primary regularization approaches that we employ in modern deep learning architectures. Each technique operates on different aspects of the learning process, and understanding their mechanisms is crucial for any serious AI practitioner. L1 regularization, Lasso. Starting from the left, we have L1 regularization, also known as Lasso regularization. The mathematical formulation adds the sum of absolute values of parameters to our loss function, L1 equals lambda times sigma, y. The key characteristic of L1 regularization is its ability to drive certain weights to exactly zero, effectively performing automatic feature selection. This sparsity-inducing property makes L1 particularly valuable when you suspect that only a subset of your features are truly relevant for prediction. Notice how the diagram shows, reduces overfitting. This occurs because L1 constrains the model complexity by eliminating irrelevant features entirely. When implementing L1 in your neural networks, expect some neurons to become completely inactive, essentially pruning your network architecture dynamically. L2 regularization, RIG. Moving to L2 regularization, we encounter a fundamentally different penalty mechanism. The L2 term adds the sum of squared parameter values, L2 equals lambda times sigma, y squared. Unlike L1, L2 regularization shrinks weights towards zero but rarely makes them exactly zero. This creates what we call weight decay, a gradual reduction in parameter magnitudes that prevents any single feature from dominating the model's decisions. The diagram correctly illustrates that L2 provides balanced loss performance. In practice, L2 regularization is particularly effective when dealing with multicollinear features, where multiple inputs are highly correlated. For most computer vision and natural language processing tasks, L2 regularization consistently delivers superior results compared to L1. Dropout regularization. The third technique shown is dropout, perhaps the most elegant regularization method in deep learning. During training, dropout randomly deactivates a fraction of neurons in each forward pass, typically with probabilities ranging from 0.1 to 0.5. The genius of dropout lies in its ensemble effect. By training multiple subnetworks simultaneously, dropout forces the model to develop robust internal representations that don't rely on any specific set of neurons. This dramatically improves generalization capability. Notice the performance curve in the diagram showing how different regularization strengths affect balanced loss. This illustrates the critical hyperparameter tuning aspect. Too little regularization permits overfitting, while excessive regularization leads to underfitting. Practical implementation considerations. For you practitioners implementing these techniques, remember that regularization hyperparameters require careful tuning. The lambda parameter controls regularization strength. Start with values around 0.01 for L2 and adjust based on validation performance. For dropout, begin with 0.2 to 0.3 for hidden layers and 0.5 for fully connected layers. Never apply dropout to your output layer, and remember to disable it during inference. The feature engineering connection. It's important to understand that regularization techniques are integral components of the feature engineering pipeline in deep learning. While traditional machine learning requires manual feature engineering, deep networks perform automated feature extraction. Regularization ensures these learned features remain generalizable rather than overly specific to training data. Advanced considerations. Modern deep learning practitioners often combine multiple regularization techniques. You might use L2 regularization on your convolutional layers while applying dropout to fully connected layers. This hybrid approach leverages the complementary strengths of different regularization mechanisms. The performance curves shown demonstrate how proper regularization creates the optimal bias-variance trade-off. Your goal is finding that sweet spot where training and validation losses converge without significant overfitting. Conclusion. Understanding and properly implementing regularization techniques distinguishes competent AI engineers from exceptional ones. These methods, L1, L2, and dropout, form the foundation of robust deep learning systems that perform reliably in production environments. As you design your next neural architecture, remember that regularization isn't an afterthought, it's a fundamental design principle that should inform your entire model development process. The techniques shown in this diagram will serve you well across computer vision, natural language processing, and any other domain where deep learning excels. Thank you for your attention. Continue exploring these concepts in your own implementations, and remember, the best regularization strategy is often a thoughtful combination of multiple techniques tailored to your specific problem domain.